In this lesson, you'll learn to write equations of ellipses and graph ellipses. Why are ellipses important in the study of the solar system? Fascination with the sky has caused people to wonder, observe, and make conjectures about the planets since the beginning of history. Since the early 1600s, the orbits of the planets have been known to be ellipses with the sun at a focus. As you discovered in the algebra activity, an ellipse is a set of all points in a plane such that the sum of the distances from two fixed points is a constant. The two fixed points are called the foci of the ellipse. The ellipse at the right has foci at 5, 0 and negative 5, 0. The distances from either of the x-intercepts to the foci are 2 units and 12 units. And I went ahead and labeled the numbers on to that one foci, and obviously it would be the same if we reversed it 2 units here and 12 to the other side. So the sum of the distances from any point with coordinates x, y on the ellipse to the foci is 2 plus 12 or 14 units. You can use the distance formula and the definition of an ellipse to find the equation of this ellipse. I'm going to buzz through this really quickly just to give you background knowledge. You don't need to write all this down. The distance between x, y, and negative 5, 0, so difference in the x's, difference in the y's, squared, square root, distance between x, y, and 5, positive 5, 0, and together that sum has to equal 14. So they subtracted this radical to the other side, square both sides, and this is a lovely thing to square out because when we square a binomial we have first term squared, first times second times 2, second term squared, but the good news is we got rid of the radical on the left side. And then we can move everything to one side. So our y squareds are going to cancel out. And we can subtract 25 from both sides and add 10x to both sides and subtract x squared from both sides. And they also subtracted the 196 from both sides, moved to the other side. And then they noticed, hey, there's a common factor of 4, so just to make their number smaller, they divided both sides by 4. And now they're going to square both sides. So again, first term squared, first times second times 2, second term squared. Negative 7 times negative 7 is 49. And the square root and squaring undo each other, so that goes away. And then they distribute, put everything on one side, or x is on one side, y is on one side, and constant on the other. And then they divided both sides by the constant they have left. So we have a general equation, x squared over 49 and y squared over 24 equals 1. And that's the equation for this ellipse. Every ellipse has two axes of symmetry. The points at which the ellipse intersects the axis of symmetry determine two segments with endpoints on the ellipse called the major axis and the minor axis. The axes intersect at the center of the ellipse. The foci of the ellipse always lie on the major axis. Study the ellipse at the right. The sum of the distances from the foci to any point on the ellipse is the same as the length of the major axis, or 2a units. And hopefully you saw that when we did the algebra activity that this is going to stretch out as far as you can go. There's your 2a units, and then as we move that string along there, it's the same string, so it has to add up to 2a units. The distance from the center to either focus is c units. By the Pythagorean theorem, a, b, and c are related by the equation, and this is not our normal Pythagorean equation, a squared, because that's our hypotenuse, minus b squared equals c squared, because in this case a happens to be labeled on the hypotenuse. Notice that the x and y intercepts are at plus or minus a0 and plus or minus b0. Satisfy the quadratic equation x squared over a squared plus y squared over b squared equals 1. This is the standard form of the equation of an ellipse with the center at the origin and a horizontal major axis. Okay, so here's a chart you're going to want to copy into your notes for reference on your homework. Standard form of an equation with a horizontal axis is x squared over a squared plus y squared over b squared equals 1. And the foci are at C0, negative C0, and the major axis length is 2a, and minor axis is 2b. When we change to a major axis that's vertical, we want to go y squared over a squared, because a shows us where that major axis is, plus x squared over b squared, minor axis again, equals 1. So our foci change. They're on the major axis, so it's vertical now, so they're on 0c and 0, negative c. The length of the major axis is still 2a, and minor axis is still 2b. Write an equation for the ellipse shown. Okay, this is nice. It's centered at the origin, so I can count. My major axis length is 5, and my minor axis I guess I should say, is half of it, is 3. So we can just plug into the formula, and we've got y squared over 5 squared plus x squared over 3 squared equals 1. And we should simplify those. So it'd be y squared over 25 plus x squared over 9 equals 1. So in their forms, they put the major axis first. I'm not sure it'd be the end of the world if you had x squared over 9 before the y squared over 25. A listener is standing in an elliptical room 150 feet wide and 320 feet long. When a speaker stands at one focus and whispers, the best place for the listener to stand is at the other focus. Write an equation to model this ellipse, assuming the major axis is horizontal and the center is at the origin. So we've got x squared over 160 squared plus y squared over 75 squared equals 1. And I used a calculator and squared those. How far apart should the speaker and listener be in this room? So we know the hypotenuse of the right triangle, and we know one of the legs, and we're trying to find another leg. It's unfortunate they used A, B, and C in a different order we're used to seeing it in, but we'll live. So using my calculator, I get C is about 141.33, and looking at the diagram, how far they'll be apart will be 2 of those C's. So they will have to stand about 282.7 feet apart. And I don't know if you have, but I've played with those at children's museums. They're pretty fun. As with circles, you can use completing the square, symmetry, and transformations to help graph ellipses. An ellipse with its center at the origin can be represented by an equation in the form either x squared over a squared plus y squared over b squared equals 1, or vice versa, depending on which is your major or minor axis. The ellipse can be translated h units to the right and k units up. This would move the center to the point hk. Such a move would be equivalent to replacing x with x minus h and replacing y with y minus k. So we've got the standard form of translated ellipses here, and the foci that go with them. Something for your notes. The good news is when we go to graph an ellipse, it's not supposed to be perfectly round. So if it looks a little potato-like, that's okay. So this guy has no minus or plus anything with our x and y squared, so our center is just at the origin. That's lovely. A squared equals 36. That means A is 6. So our major axis will be 2 times 6, which is 12. B squared is 9, so that means B is 3. So our minor axis is going to be 2 times 3, which is 6. And because the number underneath the x squared was biggest, we know it's going to be horizontal. To find our foci, we need to find C. So we're going to have C squared equals 36 minus 9. Oh, this is lovely. So C squared is 27. So C is a nice even number. 3 squared is 3. And once again, we said our major axis is going to be horizontal because the x squared had the bigger number under it. So our foci are at 3 squared of 3, 0, and negative 3 squared of 3, 0. So once again, when I graph these, I'm going to start by figuring out where my center is. My major axis is horizontal, so I went 6 units to the right, 6 units to the left, 3 up, 3 down. And if you hit those 4 points when you draw your graph, you're going to get a fairly decent ellipse. Of course, you could solve this bad boy for y and put it in the table feature. I would much rather type it as it is into GeoGebra if you want a really nice computer-drawn graph. So you can see our major axis altogether is 12, our minor axis is 6. Our foci would be at the lovely 3 squared of 3 and negative 3 squared of 3, which is about 5.2 either way. So that's where our thumbtacks would have been. Just like we did for circles, we can use completing the square to help us graph ellipses. They ask us to find the coordinates of the center and foci, links to the major and minor axis of the ellipse with the given equation, then graph. So first of all, I just sorted things out and grouped my x's and y's together, constant on the other side. To complete the square, oh, I should have factored out that 4. All right, so factor out the 4. Now we can complete the square. So we're going to take the coefficient of x by 2 and square it. So negative 3 squared is 9. And of course, it's always positive. And the same thing for the y, negative 4 divided by 2 squared is going to be 4. So I'm going to add 4 to both sides for that. Now if I write them as completed squares, I have x minus 3 squared plus 4 times y minus 2 squared equals 11 plus 13. Oh! Times 4. Okay, so 11 plus 9 plus 16 altogether would be 36. And then standard form has a 1 there, so we need to divide both sides by that 36. So when we simplify, we have x squared minus x minus 3 quantity squared over 36 plus y minus 2 quantity squared over 9 equals 1. Just like with a circle, the ellipse, our center is going to be at 3, 2. Before we can do the foci, we need to find c. So we have our equation again, c squared equals a squared minus b squared. So c squared equals 27. So there's our lovely 3 squared of 3 again. So if we want to go to the left of the center, it's going to be 3 minus 3 squared of 3. And if we want to go to the right, it's going to be 3 plus 3 squared of 3, 2. The major axis is the square root of 36, which is 6. And the minor axis is the square root of 9, which is 3. So once again, to graph, we're going to start at the center, which was at 3, 2. And I'm going... my major axis is, ooh, I only did the semi-major axis. I need to take that times 2 and times 2. The really useful thing is what I had written there, because my semi-major axis tells me I'm going 6 units to the right, put a point, 6 units to the left, put a point, 3 units up, 3 units down. And then connect the dots with hopefully a nice smooth ellipse. For a concept summary, they just gave us the standard form of the equation that's been translated for both a horizontal and vertical ellipse.